Good morning, good afternoon, or good evening. This is a full paper workthrough of the 2024 Discrete Paper 2. Need a funny name to start. Aim of this, of course, is to give you, one, some solutions, but also hopefully show the kind of thought processes that will aid you working through a paper like this, both for your revision and for your review of such papers. Now, discrete isn't something that I've taught recently, so I might be a little bit slower or make more errors with this, but let's jump straight in. Our multiple choice questions first. And straight away, I know there's a really good rhyme for this. I don't remember the rhyme. What I do to remember this one is to consider a cube and just recreate the formula. So a cube has 8 vertices, 12 edges, and 6 faces. And the way to make that work with a random 2 popping in is v plus f equals e plus 2. So I'm looking for the one which has a negative e. And that's how I remember that formula. 2, some more graph theory. Find the expression for the number of edges of the complete bipartite graph. So that has m there and n there. If we count how many edges, every single one of those has degree n to match with every single one of the others. That has to be m times n. Which of these is semi-Eulerian? So an Eulerian graph you can draw completely without lifting your pen or pencil. So that's Eulerian. A semi-Eulerian has to have a fixed starting point and a different starting point to end point, which is that one there. The condition being that there's exactly 2 odd vertices. We have our Cayley table, now multiplication modulo 5. Mod 5 multiplication was the remainder when you divide by 5. So 1 times 1 is 1, 1 times 2, 1 times 3. Those ones are all fairly simple. 2 times 2 is 4, 2 times 3 is 6, which leaves a remainder of 1. 2 times 4 is 8, remainder of 3. It is symmetric, so we can cheat a little bit. 3 times 3 is 9, remainder of 4. 3 times 4 is 12, remainder of 2. And 4 times 4 is 16, remainder of 1. The identity element does nothing when you multiply by it. Well, almost always that's whatever the 1 is. State the self-inverse. Self-inverse is where you combine to get back to the identity. And it's the only one which has a 1 on that main diagonal, except for the identity itself. The identity itself will have a 1 there. We don't say the identity is self-inverse because it's already the identity. Straight on to question 5 already at blistering pace. Question 5. We have a network. They represent distances. We want a minimum spanning tree. Okay, well, this feels like, well, we can use Kruskals or prims. I'm going to go with prims just because it's slightly easier to draw. So if I start at A, the best is to C. Then from C, the best goes to E. From that whole combination, I've got an 8 to D. I am trying to put them roughly in the equivalent spaces. So I've used a 12, 13, 8. My next best looks like a 14 from B. Now I'd like to use the 15 from A, but that will create a cycle, so I can't use that. I can see an 18, which gets me to F. I think that's my next best. And finally, I haven't got to G yet. So that's a 19. There were 7 vertices. I've got 7 vertices in my new one. Quite an odd question. Normally they enforce you to at least keep track of the order you put things in. Total length, grab the calculator, add up all of those side lengths, and we get a total length of 84, and it's in miles. 84 miles for this minimum spanning tree. Oh, and that was the whole question. Very surface level context there. Didn't actually have any impact. We now have our linear programming question. We're selling two types of cakes, blueberry and chocolate, and there's some conditions. We wish to maximize the profit. So first thing we need to do is introduce some variables. So let B be the number of blueberry cakes sold, C be the number of chocolate cakes sold. So I've got my setup. So now I need to put my objective function. I want to maximize our profit, so let's maximize P equals, well, our profit is 20p per blueberry cake, 15p per chocolate cake. So I want to maximize the expression 20b plus 15c subject to, and this is where we need our conditions. We want to sell at most 200 in total. So B plus C has to be at most 200. And so I've used that statement, I've used that, I've used that, I've used that, I've used that. So finally is that last bullet point. Sell at least twice as many blueberry as chocolate. Sell twice as many blueberry as chocolate, at least. So I want lots and lots of blueberries. B has to be greater than or equal to 2C. And then there's the trivial couple of statements. We need B to be greater than or equal to 0 and C to be greater than or equal to 0. There's no point trying to make negative amount of cake. And that seems to have covered all the aspects, and that's about 4 marks worth of writing. Binary operation question. We have A triangle B. Well, that's actually the symbol delta. That's a capital delta in Greek. Is A plus B plus AB. Determine whether it is commutative. Justify. So the commutativity statement is whether the order matters. So A plus B is A plus B plus AB, which I can write as B plus A plus BA as addition and multiplication are commutative. I've swapped the order of those operations. If they weren't commutative, then a lot of lower level numeracy just wouldn't work. And then that is exactly what B triangle A is. So therefore, A triangle B is B triangle. Oops, my triangle's upside down. Is B, I should say delta A, I is commutative. Prove that it's associative. Associative is a little harder. Associative is the brackets condition. So we need to try and show that if I put brackets in one spot, it's the same as putting brackets in the other. Now this one just is it's painful. You just have to be very careful with your algebra. So A delta B delta C. I need to do the B delta C first. B plus C plus BC. Excuse me. And then let's do A delta that thing, which is A plus that thing, plus A lots of that thing. Expand it out. We have plus BC plus AB plus AC. And there's 2 ABCs that come out. No, there isn't. I was interpreting the first one as a bracket. It was not a bracket. It's just a single ABC. So I should have 1, 2, 3, 4, and then another 3 from the bracket. I should have 7 terms. I do have 7 terms. Okay, so that was if the brackets were that way round. Let's check if the brackets were the other way round. This term I need to do the A triangle B first, and then triangle with C. Well, that's add them together. Again, I'm putting brackets around to make it obvious that that is a single term being considered at that point. And finally expand and simplify. Expand that second bracket gives me all of these weirder terms. And shock horror, those two things are the same. So now we just need to write our conclusion. So A triangle B triangle C is A triangle B triangle C. Therefore, triangle is associated. Now, if I really wanted to be official, I should also put at the end here for all A, B, and C. There was nothing about A, B, or C that was special, and it does need to hold for all of them. And I should also do the same up here as well for all A and B. A and B weren't special to make that work, it just always worked. And that was all of that question as well. Question 8 is our network flows. The circled, the uncircled are the capacities, the circled is a feasible flow. The initial flow through S to D is 8. Okay, explain why. So, let's look at the sink first. At the sink, the flow is 12 plus 3 plus 10. So that's those 3 circle numbers there. Oops, let's not undo the work I've actually done. So the flow is 25. Well, that means that the flow at the sink, sorry, we've just done the sink, the flow at the source is also 25. But that is the circled numbers again, which is the 10, the 8, and the x. Well, that's exactly what the information we need to therefore say as 25 equals 18 plus x. So x equals 7. And I've been a bit, I wouldn't have written so much if it just said find x, but because it was an explain and show that, it was worth doing a bit more work. State the value of y. So now I've got that this is a flow of 7. But if we look at D, 7 is going in, 2 is coming out, so the rest has to go along there. Well, that means there's 5 going out there, so y equals 5. State the value of, state the value of z. So where is z? Good question. Z is up here. So I want to try and find this z here. I now know that y here is 5. So same argument. I've got 2, 8 and 5 going in. So I've got a total of, almost messed up my mental arithmetic, I've got 15 going in, going out. I've got z plus 11. Well, then that's just telling us that z is 4. Prove that the maximum flow through the network is at most 27. Well, I've already seen a flow of 25. That's what's currently in the picture. And the fact that we should remember here that max flow is equal to min cut. So if we can find a cut of 25, then of 27, sorry, then we're sorted. So let's look for a cut of about that size. Let's go to my annotations for clarity. Can I find a cut of 27? And I've already kind of seen that there is the maximum is 12 plus 5 plus 10, which is 27. Is less than or equal to the cut that splits t from the rest, and that is a cut of 5 plus 12 plus 10, which is 27. So the maximum flow is less than or equal to 27. It didn't want us to show it was 27, it was only at most. Now to show it was 27, we just need to find it. And probably the easiest way to do so is to find 2 extra that can go through the system, and we can add an extra 2 along that path there. None of those are a capacity. I might have preempted. No, I didn't preempt the next part of the question. There was no next part of the question. Our resource management now, our Gantt charts. Robert is working on a small project. There's going to be a lot of sliding backwards and forwards. I apologise on this question. Into 10 activities with those durations. On the opposite page, construct an activity network and fill in the earliest and latest for each. And it's on its side as well. Now, if I do that, that means I need to write on my side. So unfortunately, I'm just going to write the right way up, and you'll have to tilt your head. So I'm still going to have to tilt my head for this though. So we need to fill in the rest. So C and D both depend on A. So I need to put a box C and D. Apologize, they're not amazingly shaped boxes, but that's okay. E depends on B and D. So let's put E in B and D. F and G both depend on E. So there's an F and G. I'm not going to be able to write a number in that space. F and G depend on E. H and I depend on F. H and I. Got very inconsistently shaped boxes, depend on F. And then finally J depends on C, which hasn't been used yet. That's J. H, I, and G. So all of those then depend there. Durations 1, 1, 10, 1, 1. This is where I'm going to have to make boxes or just zoom in. 10, 2, 5, 6, 2, 5, 6. G is 1, 1, 1, 1, 2, 4. Okay, so now I can start. Can I now tilt the screen to make your life easier? Does that work? Which way makes it the right way up? Does any way make it the right way up? No, unfortunately not. So I'm going to keep it that way. I apologise. I'm not entirely sure how to make that the right way up on the screen, copying across. But now I need to put in my earliest and latest times. So the earliest that those can start is 0, which means the earliest that C can start is 1 after A is finished. So actually change the colour so it pops a bit better. That's not a good colour. So you can see outside my boxes, D can also be latest of 1. Now E has to wait for D to finish. D finishes after 3 units of time. F and G only depend on E. Started at 3, moves an extra 5 forward in time. H and I only depend on F. That's 8 plus 6. Then finally J. Well, C is a restriction of 11. G is a restriction of 9. H is 15. I is 16. So the earliest there is 16. And now for the latest finish. Well, the latest finish J can be, we want it to be as early as possible. The latest it can be is 20. Now we start going backwards. So H needs to be finished by 16. 20 minus the 4. 20 minus the 4. 20 minus the 4. And same for C all the way over here. Now F. F needs to be finished for 16 minus 1 or 16 minus 2. 16 minus 2. Otherwise it will restrict I. Then E, well, 14 minus 6 or 16 minus 1 is 8. That forces D. D has to be finished by 3. A has to be finished by 1. And B can actually finish as late as 2. B finishes at 2. No, 3. Sorry, mental arithmetic. 8 minus 5. That could be as finished as late as 3 for E still to be on track. Okay, so now I assume it's going to start talking about the critical path for the shortest about time. No, again, I'm surprised. I feel like a lot of... Oh, I haven't actually gone back to this section. Robert claims that the project will be completed in 20 days. And yes, indeed, my earliest finish time is 20. Comment on validity. Yes, it can finish in 20 days. Now 2 marks makes me feel a bit uneasy that that's enough, so I'm also just going to put in the critical path. Whether I get the mark for it or not is no effort. With critical path, so we're looking for things where the start plus the duration is the final. So that is that sequence there. A, D, E. Gosh, that's a lot of letters. A, D, E, F, I, J. Of length. So I'm just doing the mental check. A was duration 1, D was 2, E was 5, F was 6, I was 2, J was 4, which does indeed add up to 20. So we have a critical path of length 20. We cannot finish quicker than 20, and that diagram showed that we can actually do it in 20. Question 10, game theory. The game represented for Bilal, x is an integer. It has a stable solution, so there's only one possible value for x. So x is an integer. So to have a stable solution, our minimax and maximin have to match up. So to play safe, we want the minimum of each for Bilal. It's -2, -3. And we don't know for the last one yet. We don't know if the smallest is -1, x might be smaller. And then let's also consider the max over here for don't know and 1. Well, to make a stable solution, our maximum minimum, so what's that, our row min, has to equal our column max. So the maximum value has to match the minimum. So feel like I've got that the wrong way around. So let's think about that again. I want the row, I like the phrase maximin. The maximum row minimum has to match the column minimax, the minimum column maximum. Well, that means that this kind of has to be the x's. And the only way to match these up, because none of the rest at the moment match up. Well, so that means to me the minimum, so for B3 min, well, that's going to mean that x has to be smaller than -1. But then to be the row maximin, x has to be greater than, can we be equal to? I suppose these could be equal to's. Has to be greater than or equal to -2. So that's doing it from Bilal's point of view. From Mayon's point of view, for M2 maximum, x needs to be greater than or equal to -1. That's already put a restriction. And then the column minimax, x has to be less than or equal to 1. Now, I feel like I'm not showing this. It feels like I made some assumptions to make this work. Which feels a bit awkward. So let's follow this through and let's look at the kind of conditions to make this be the situation. So with those inequalities, that implies if x is less than or equal to -1 and greater than or equal to -1, then x equals -1 for the stable solution. B3 versus M2. Now we've been told there's a stable. Now it didn't have to be that combination. And that's what I am kind of worried about. So we only have 1 mark left in the paper. So my concern is, what if the stable solution was elsewhere? And that feels quite difficult to check. Well, we could go through each combination and see why it's not possible to be stable. So example, the M1B1 cannot be stable because Bilal will prefer to move to B2. This feels like a lot of effort to show that clearly, but maybe it isn't. Yeah, maybe it isn't. So if we go through all of the combinations, writing this is quite awkward as well. This is one where I'd like to speak to someone who knows discrete a little bit better about how what they expect from a question like this. So that one is not stable because of B2. Would swap to B2 if we had the choice. The B1 M1 is not stable because we'd prefer to swap to M1 if able. M1 is better for Mayon than M2 is. M3 would prefer, yeah, again, we'll prefer to swap to M1. So in all those situations, we'll prefer to swap. If we're picking B2 M1, then we'll prefer to swap to M2. If we're M2, we'll prefer to swap to B1. -1 is less worse for Bilal. Then finally, M3 would prefer to swap to that's M1. If that's not stable, because Mayon will prefer to play M1, and then B3, M1. Bilal will prefer, if that was stable, Bilal will prefer to move to B2. B2 is better. And then we'll skip the one with the X in B3, M3. We'll prefer to go to M1 again. -1 is better for Mayon than that. So that implies that M2 versus B3 is the only possible stable, because we've been told there's a stable solution, so that's the only possible one to be stable, and then it all works above to find the value of X. Again, I feel like that's a bit excessive of an argument at A level, but then again, this is the very last question, so I'm not surprised if it did. Maybe the stuff in black was enough. State the value of the game for Bilal. So if we're stable on that X, the value is his expected outcome. He's expecting to gain X every single time, and we've already said that X is -1. So the value of his game is -1. That is that entire paper. Hopefully you gathered some useful ideas and thought processes out of that. And of course, if you have spotted any error on my part, please do let me know, and I'll happily check and confirm and correct as needed. Otherwise, good luck with revision, and I'll speak soon.